Hello, everyone. This is Deli. It's great to be here. So today I'm going to share a topic that we're quite familiar with, and I'd like to really bring up again regarding the TEs in Ethereum. So we'll actually go over some of the trusted execution concepts, and also we'll dive into what kind of role TE gonna play in Ethereum and also in general in Web3. We're going to reviving some of the original principles that Ethereum starts with. So by the way, I'm Deli. I'm the co-founder of Automata. We're actually building a verification layer for all kinds of trusted execution environments. In essence, actually, Ethereum has a lot of first principles when it was founded almost 8 years ago. Some of the principles include decentralizations, such as privacy, transparency, as well as trust minimizations. One of the more prominent one that coming out recently is actually censorship resistance. Ever since we started transition from proof of work to proof of stake, this has been a really important topic. And when MEV issue comes up, people are also discussing how those builders and also the players in PBS could play a part to prevent this kind of censorship from happening. Also, of course, there's tons of permissionless innovations going on, but still there are challenges as well. Also, they're just coming up along the way, scalability issues. That's why we have to take the L2 route to scale up Ethereum and also its ecosystem. And also privacy issue, people are using Tornado Cash for to hide the trace of the money, but there should be better tools that maybe more aligned with the compliance. And also fairness issue, of course, because there are chances right now, because of MEV issues, if your transaction might got treated differently from others if you're not tipping enough in your transactions. So then when it comes to the context of 2025, actually there has been quite a lot new primitives coming up. It's getting mature over the last year. We've seen a lot of rollups using zero-knowledge stacks. Also, we've seen projects trying to create MPC protocols, FH protocols as well. Of course, we are actually building a trusted execution environment. We are trying to use this kind of a hardware-based security to make Ethereum better. So one of the principles we are aware of is actually, although this kind of attack is still hasn't been adopted by the mainstream, but it's still it's something that we'd like to be more practical with. We'd love to see new applications coming up. Also later on we will review a few that already exist in Ethereum ecosystem. So actually, what is TE, or Trusted Execution Environment? So TE is actually an isolated region in the hardwares that helps you to isolate your the code and data from other operating environment. For example, if you use Intel SGX, it helps you isolate your applications from even the operating system, so that nobody, including the OS, including the operator of the node, can see what's going on inside your program, essentially. Of course, there are other types of TEs as well. For example, recently, NVIDIA also introduced TE into their H100 or H200 GPU, which makes it capable of running LM inference privately. We will also touch on this topic later on. Essentially, TE provides several very useful guarantees. One of them is actually confidentiality, because by nature it actually isolates the execution from the normal mode, so nobody can really see the code that's being executed. Also, the memory regions are isolated as well, so this is really a private enclave that only approved users can access. Of course, there will be one also important component called remote attestation. This is actually essential to verify all the claims that we have. For example, if I can present a proof that's showing that I'm actually running the machine, also I'm actually running the piece of code that you're expecting. So this is going to be some attestation that you can verify even remotely. Of course, right now we are seeing that most of the modern hardwares are actually capable of running this kind of special mode. You can see this kind of attack in like some of the cloud computing stacks, as well as your even like local machines, local devices, including your phones or even your laptops. So if we look at the broader picture, like what's TE looking like in Ethereum today, there are actually very good examples and also applications running in production. First of all, I'd like to also give a shout out to Flashbots because they've been really like exploring the like the frontiers of using TE to solve some of the MEV issues. I think lately they just brought this entire builder net in production, which consists of like builders that are entirely running in TEs. It gives some guaranteeing that you can really decentralize block building and also provide the guarantee that the transaction won't be reviewed until it's finally executed. Also, there has been development in the rollup space using TE as well. I think throughout the whole last year, we've seen many people, many rollups, especially ZK rollups, taking a step on like using TE for additional proving. Essentially, they're just running all the L2 blocks, L2 transactions inside the TE environment that essentially just emulate the transactions, but generate kind of a correctness proof to double check whatever result that ZK circuit has generated. This is mostly used for like preventing like a single point of failure because, as we know, ZK circuit might still have some kind of unknown issues which could potentially jeopardize all the assets on rollups. Of course, we've also seen Flashbots develop this rollup boost framework that helps reduce block time and also provide verifiable priority ordering on networks like Unichain, which is a rollup network, OP stack based, created by Uniswap. Also lately, WorkCoin has launched WorkChain, which tries to prioritize the block space for humans. I think they are also using the rollup rules that are created by Flashbots. As you can see, many rollups has actually adopted this approach, which means TE has been used in the rollup space to secure at least millions of dollars values on chain. So this is maybe I can extend a little bit on like how multi-prover really works in TE. Essentially, you're gonna have different types of proof system that you can make use of to make sure when one of the proof system has issue, there will always be like replacement. Of course, you can also run multiple proof system in parallel so that when in the end you can really see maybe a committee of like different proofs and make a decision out of it. So it actually really greatly like reduce the single point of failure of any rollups and also improve kind of the trustworthiness a lot. Also, I'd like to continue other examples as well. I think we've seen new kind of development like from WorkCoin. They're actually building their newly created anonymous MPC service to help like prove the humanity of like people. Basically, they are scanning the iris code. They are getting the iris code from their like ops. Eventually, they will try to decide if this is one of the new code that they haven't seen before in their database. So what they're doing is they're actually running this database across like a MPC protocol, which requires a TE setup because you'd like to have this kind of thing to prevent any collusion attacks because this was kind of a known issue in the any of the MPC protocol. And of course, we have seen projects building in the composability space. Like they are trying to use TE to like make fast confirmations, create real-time proofs as well. Lately, I think EigenLayer has also mentioned that they are building autonomous verifiable services, which can also make use of TE coprocessors to kind of scale up the computations, to provide service for rollups, as well as for the like AI agents as well. So if you like to compare TE with other technologies that we have seen in the previous slides, there are actually good sides and also bad sides. But I think we have to really understand like what are the kind of the best fit for this kind of applications. I think one of the really good strengths is TE is really performant. Compared to running applications in the normal environment, TE actually doesn't add a lot of overhead. When it comes to using maybe ZK or MPC protocols, it's actually significantly more expensive to use. Not even to mention that there's cost in the proof generation as well as proof verifications. But on TE, it's actually very like to verify the attestations is also very like affordable on chain. But we have to also understand that there are limitations too. For example, like if you are using hardwares, you can't really circumvent this issue, which is you have to trust the manufacturers, such as Intel or AMD. So this is one of the things that has been kind of the blocking some of the usage in blockchain, because if you really want to build a like secure protocol, chances are you'd really try to remove any dependency on centralized parties. But if your trust model can accept this kind of a setup, I think this is actually an acceptable way to go. So actually, to mitigate some of the like issues that people have brought up about TE, there has been quite a lot of different defenses. For example, at least you can start like rotating your keys to prevent to prevent some of the side channel attacks, because when the times come that the keys are extracted, maybe the key is already expired, so it's kind of like bypass this kind of attack vectors. Of course, you can avoid like storing long-term secrets in your TE, because like I think we all have consensus that maybe one day TE gonna break. It's better to stay on the safe side. So even if it's broken one day, if your secret is not a long-term, it's a informal key, you are still gonna be on the safe side, because all you need to do is just revoke the key and continue. Also, there are other like mitigations you can do, like reproducible build or even like open sourcing your code to really let people verify all your claims in the attestations. Right, and next I'd like to also discuss actually real-world usage of TE, but it's actually coming from the kind of the traditional Web 2 world, which is Apple. They have been using TE to create their private cloud compute technology, which essentially helps you to like run more like powerful and advanced LLM models on the cloud, but still preserve privacy. How did they do this? They actually use specialized operating systems running on their own Apple Silicon hardwares. Essentially, they're creating their own server specs so that they can run this kind of TE-capable hardwares. Then they are trying to process the data between your like personal device and the cloud node, so that only the like your device or even you will know the data that you're sending over to the node running in their cloud. And of course, they have like all the transparency logs that over there that you can verify all these kind of guarantees. So it's actually quite powerful, although like some of the components are actually still closed sourced, but I think it's actually one of the kind of like most complete like TE cloud-based TE applications, which gives us a lot of inspirations when building similar solutions in the Web 2 space or Web 3 space. So when it comes to the TE acceleration, we've seen that there are many existing use cases, but we'd also like to explore some of the like futuristic ones. For example, this is something that we're building. We're trying to create a verifiable and privacy-preserving RPC, so that when users visit the RPC nodes for blockchain data or even for LLM like response, their private information won't be collected, and also they will know that the data source is trustworthy. Of course, there are also like other really interesting use cases, such as building a private DeFi protocol, or even a fair markets to settle the transactions. And also, if you are really keen to like exploring the AI agent space, there are teams also building like verifiable AI agents or autonomous AI agent that are fully running in TE, including the agent framework as well as the AI models, which provide a really strong guarantee in terms of the privacy of the data and also the verifiability of the model. I'd like to also address some of the actual concerns again. If you have issues with like hardware trust and have concerns on like centralizations of the maybe the manufacturers, there are a couple of ways to actually to avoid this. One of the thing is at least you could use multiple different TE vendors. There are already like a lot of technologies out there. If you use two of them, you will at least have a better guarantee, because it's hard to really break all of the maybe two of the like TE technologies out there. Also, you could start like really embarrassing like open source TE solutions. There has been research effort on like creating an open enclave, maybe for example the Keystone projects like in the RISC-V space. Also, as a developer, you could really think about create like more fail-safe design. So when like even in the most extreme cases, when like all the TEs break, you still have kind of a fallback that will not harm users. For example, you could still have ZK as one of the fallback solution. It's just a little bit slow, but still nothing will eventually break, because it's kind of the it's gonna save all the like the data over there. Also, like people have been talking about like security vulnerabilities. Also, there are new reports coming up in especially maybe like Intel hardwares and AMD hardwares. So for those, I think as long as we can patch those firmwares as soon as possible, also like have really good secure SecOps. Eventually, these are all like non-issues to like running a like TE environments, because essentially these are some of the challenges we have to overcome. Of course, to really like convince people that you're really running good hardwares and also the like codes in the code bases, you have to also produce like attestations properly. Really trying to verify those attestations even on chain or off chain to convince other people. Also, you could you could try different like offerings from different cloud providers, which provide additional redundancy. You could also have like new hardware support like coming up from NVIDIA GPU, which helps you to run private LLMs in hardwares. So actually, there has been also quite a lot of resources right now. If you want to get involved in like TEs in Ethereum, especially, you could really like go to some of the forums over there. It's actually contributed by most of the TE projects that I've listed on the screen. Right. So essentially, TAC is more like a social campaign right now, because we know that there's pushbacks coming from the community, coming from the researchers, but we're really trying to come together and trying to show that this is really a more practical approach when it comes to some of the issues that we're facing, no matter it's the scalability issue, no matter it's the privacy issue. Also, like we've seen that recently, all the AI-based compute, it really requires a lot of computation powers, which might not be a good fit for other solutions. But at least we've seen the effort from like all the hardware vendors to try to make it happen, so that we can really have a more safe environment for your like AI workloads. Yeah, so we would hope that in 2025, we will see more applications coming up, like using TEs, and we'd like to see more cross-stack applications as well. So maybe using ZK with TE, or maybe using MPC with TEs. These are really interesting solutions that we look forward to. Right, I think we are coming to the end of the talk. If you have any like things you'd like to know, please follow us on the socials or get connected with us. If we have, maybe we have 1 minute over here. If we have questions from audience, please raise your hand. Okay, if not, I think that will be the everything for today. Thanks, everyone. It's really glad to be here.